but it's only been a good study. To be honest. This one I studied like a lot.
I didn't study that one.
I studied it and still got. I feel like I did that. So, I'm just gonna stop coming to class and just watching all the lectures on my phone. He's not helping me at all. I don't think I'm and I found like you can see how it goes. Maybe I do this.
I get that.
I have to do the other thing myself. Next exam, I have to
I'm trying to like keep doing well now, so I don't get stressed.
try no, yeah, I'm definitely not.
Given how my labs too. Given how my
Story list, it's so weird. I either do really good on my finals or I do really bad. Like last semester, my grades were all good, but then the finals came, and then it dropped like an A became a B, and then like a B became a C, but I didn't even see. But then it dropped, and then the semester before that, I got all A's, even though the finals were hard. So I didn't know. I don't know what. How many did you say it was back?
I got to the first and I'm like,
Not either way.
and then I just guessed that I knew that was the one. So I had like X minus yeah, factored out.
That was out of 3 points that really got I just one but see I didn't even I don't even remember. Number 2 I think number 2 was shorter than I thought. Was it short? Okay. Because I was like, there's no way like this question has 8 points on it or 6 points on it. It's too short.
I probably should have factored time on that.
Yeah, I think that's the only one that I finished.
Make sure I got that.
I think I got maybe that one, but it's just too short. Some people just think also, I didn't have enough time. As per usual.
oh my goodness.
I shall go home and kill myself later.
Yeah, another. I don't know. Yeah.
Okay, good morning everyone. So I want to very briefly talk about the exam that will be next week. This is your second midterm exam. First things first, topics for the exam. So you will have 3 to 4 problems I would say. Okay. The problems can be on the following topics. Axial loading is one. And in axial loading we have seen several different things. You've seen statically indeterminate structures, method of redundant supports. And the method of redundant supports. Then we've also seen thermal stresses. That's a part of the exam as well. So you could have 1 or 2 problems on these. You will be asked to draw the state of stress, calculate displacements and so on. Okay, similar to what you've seen in the homeworks. And then we go to torsion. In torsion, I'm going to upload your homework solutions for homework 7 and 8 very soon. In torsion, you're going to have problems on angle of twist, calculating the shear stresses, and also for statically indeterminate torsion with distributed loading. Okay? So angle of twist. Statically had thought to include shear force and bending moment diagrams as well, but I believe that's going to be a little too much. There is enough information for us to work around for this exam. Torsion is particularly challenging, okay, and I've seen that in some of your homework solutions that I've been going through. I feel that this has not been registered too well. So I'm hoping to have a review session before your exam, like we did last time. It will be on Zoom. It will be over the weekend. I'll record it and then I'll post it on Cover. Okay, I'll send out an email regarding the actual time for this review session. Okay, so there will be no shear force and bending moment diagrams for this exam, but for the final exam, it's going to be pretty comprehensive. We're going to have a lot of focus on shear force, bending moments, calculating bending stresses, calculating shear stresses, and two more topics that we are left with, which is what I call as combined loading and then principal stresses. Okay? And you need to know how to draw the volume elements as well for all of these. Okay, so volume elements. For both the situation. And as it stands, the exam is going to be next week Monday, as it stands. I sent out an announcement yesterday saying that, okay, rather than have the exam on Monday over a constrictive period of time, like 1.5 hours, I would like to open up this exam on Tuesday between 12 in the morning and 11:59 p.m. in the night on Tuesday. You can select 3 hours of your choice. Exam is not going to take 3 hours. It will be of the same level of difficulty as midterm 1, but you will have 3 hours to solve the exam. And that is the option that I have presented to you. I have heard back from a lot of you, mostly in favor of this option. There are, I think, at least 1 or 2 who believe that perhaps they have commitments on Tuesday. I will go with the majority opinion. We are in a democracy still. Okay? How many of you in this class are for this idea of having it on Tuesday for a larger span of time? Okay. So are there any reasons as to why you think the people who did not raise your hands, and this is completely fine, I just want to know your opinion. Why do you think this may not be a great idea? Yes, sir.
So you said there's going to be 4 questions for this exam?
3 to 4 questions, right?
Because one of the questions took me like an hour and 15 minutes.
So
and that was just one question.
That is an individual perspective, right? And here's what I want to convey. You have to time yourselves. Okay, you have to be very brutally honest with yourselves. Am I knowing the material really well on the top of my head, at the tip of my fingers? If that is not the case, if the material is not going to flow, it is going to take time to solve these problems. No matter how much time I give you, 24 hours, it's going to take 24 hours. The longer I stretch it, the longer that's going to take. Okay? So you have to be on the top of your game. If you're on the top of your game, this exam is doable within an hour. Granted, last exam probably I could have cut back on some material, so I will be taking it on a case-by-case basis. And I know that a lot of you had the issue that you knew the material, but you did not have enough time to maybe portray your understanding of the material. So which is why I'm trying to alleviate the situation now and say that, okay, I'm going to give you 3 hours. Have a decent crack at it. The exam is not going to take 3 hours, for sure. Okay, this is my promise to you, but I'm not you. I cannot sit down and say, okay, I'm going to complete the exam in an hour and a half. If I'm given 3 hours, I'm going to take the whole 3 hours. Okay, I'm going to go slow. I'm going to keep checking each and every step of my work, but it will be a fair game. That is my opinion. But majority of you, whoever I want to give the option. Any other thoughts on this? Are people against this? It's completely fine. I mean, this is just an opinion. This is a discussion. I'm fair to having constructive views on things. I don't want to bulldoze my way and say, okay, this is what you've got to do. If there is enough resistance, and if the resistance is stiff, then we will just go for Monday, an hour and a half, get it done with. I have no issues with that. So, yes, yes.
I just think for people who have like work and extracurriculars outside of class,
That is an issue that that is an issue that I've been wrestling with, and I'm thinking, is it possible for me to open up the exam from Monday to Tuesday, so that people who have maybe commitments on Tuesday can write the exam on Monday within 3-hour interval.
I was
Yes,
gonna suggest like doing that 3-hour period, but on Monday instead of Tuesday, but like doing it the whole day on Monday, so we can have like the night of Monday to work on it maybe if you want to, or.
That is also completely fine with me. I mean, I'm open with both. The only reason why I wanted to, so my thinking is that, okay, if I don't do it on Monday, I'm saving a lecture up when I can come and, solve some problems and so on, so that we continue to learn more topics. So that was my reasoning for having it on Tuesday, but I'm completely fine having it on Monday for 3 hours. You choose your time block and then you go for it. Yes, sir. That was my thought. So I'm more inclined to having it open from Monday all the way up till Tuesday night. So Monday morning 12 o'clock, all the way up till Tuesday night 11:59. You're going to give me your word of honor with the honor pledge that you write, that you will play it fair. I will play it fair. You choose a block of time that satisfies you, 3 hours on Monday or 3 hours on Tuesday, you write the exam. Does this make more sense to everybody, so that you don't, and I'll still have class as usual on Monday. Is that okay with everybody? And it's your choice. If you want to come, you can come. Otherwise, you can watch the recorded lectures. That is completely fine with me. If you want to write the exam during the class time, that's also fine with me. Okay, but not here, of course. Does this make more sense to everybody? Is this something that you'll all be okay with? So if you have things to do on Tuesday, completely understandable. I mean, we all have things to do in whatever sphere of activity that we are involved in. So my inclination, as of now, is to open up the exam on Monday morning, 12 a.m., and open it up all the way up till Tuesday, 11:59 p.m. You select a 3-hour window. You have only one shot. I want to make it very, very clear. You open up that exam, you have only one shot, you're done. Okay? That's the same thing with the exam, whether it was 3 hours or 1.5 hours, you're still going to have only one shot. Okay? So you're going to have one shot, you get it done, 3-hour interval or window that you want to choose, go ahead and do it. Now I want to see how many people are okay with this thought. Show of hands, maybe. Okay, so people who had initially opposed this idea, is this fine with you all too? Okay. Exam will be fair. I'm not going to unduly increase the length of the exam just because I have 3 hours. I'm going to assume that you're going to solve this exam in an hour or an hour and a half, max. Okay, the exam is not going to be taking 3 hours, but here is the deal. If I were you, if I were a student, and I'm still a student in many ways, I'm learning every day, if I were a student, I would make use of the entire 3-hour interval, think my way through the exam, take my time doing the figures and everything, and make sure my calculations are correct. Even though the exam will not take me 3 hours. Okay, so this is something I want to mention. Yes, a question?
Did you say when are you uploading the practice midterm?
I will be doing it tonight.
Tonight, okay.
I'll be doing it tonight. I still owe you guys homework solutions for homework 7 and 8. At least part of homework 8. The shear force bending moment, we're going to do it only for the final exam, and so on. Okay? So these are the topics. I would be particularly, if I were a student preparing for this class, I would make sure that I understand the distributed loading in torsion really well. Okay, how to cut it, how to obtain the expressions as a function of the distance x, and then how to obtain the shear stresses based on that. Okay? And drawing of the volume elements and so on. This is always the trickiest part of the exam. This is more or less straightforward. You can have a gap problem with thermal stresses and axial loading, like a combined problem that we've done in class, we've done in the homework. Not much of a thought in that, right? You just have the load applied, you have the temperature effects applied, you combine them together using your compatibility condition, choosing one end of the support to build up. Okay, so one problem of that sort. The other problem will be on torsion. There will be a little number of parts. I'll make sure there aren't too many subdivisions in each problem. I think that was the issue last time. There were too many subdivisions, and probably people are stuck up in one or the other, so you couldn't go to the next one. All right, does this make everybody happy? I want you all to be happy. Mechanics may or may not be your cup of tea, but I don't want to have anybody coming off of this class with a sour taste. Okay, so it's a cup of tea anyways. You may or may not like tea, right? So I hope that this is a measure that reduces stress. I know that a lot of us are really good at certain things, but if you are constrained in an artificial way to solve something in an hour or two, I believe that is injustice to everybody. Okay, so I feel 3 hours is a sufficient amount of time for an hour-long exam to be solved thoughtfully, carefully, and with some interest. Okay? All right, we're going to continue with the lecture as usual. So I'm going to talk about bending stresses briefly from where we stopped last time. Then I want to talk about shear stresses due to transverse shear. And then we are going to close up shop on all of these derivations and then just start solving problems on Friday. Okay? So today also there will not be a derivation. I just want to present the formula. You're going to take it as a matter of faith. You have belief in me, I hope. And we will just continue with our thoughts on it. Okay? So from last time, bending stresses. We have a beam. Assume that the bending moment is applied in the positive sign convention. This is the bending momentum. As of now, I am assuming a rectangular cross section. Okay, so this is just for simplicity, but we are going to look at different other types of cross sections as well. So I'm having a rectangular cross section. The width of the cross section is W, the height is, or the thickness is 2 times T. Little t and little t. My axis, it is very, very important to have the following axis because we are going to define a direction for stress. Now we are going to ascribe a direction for stress. Okay? So here is my, what is this called? This is called the neutral fiber. Right? This is the fiber along which there are no bending stresses. Okay, so this is the neutral fiber. And for me, typically the x-axis is along the neutral fiber. But I can come tomorrow and change it and call it as a z-axis. That is completely fine. Axes are for our convenience. X-axis. This is the y-axis. Okay. So I have the x and the y-axis. The axis coming out of the page is the z-axis. So right up here. Which means that if I'm looking at the cross section, the axis that I'm going to see is I'm taking this guy, flipping it towards you. So the x-axis is going to be pointing into the board. The y and the z-axis are what you'll be seeing on the plane of the cross section. Here is the y-axis. And here is the z-axis. And we said last time, the intersection of the neutral fiber, or the plane containing the neutral fiber, which is the neutral plane, and the cross section gives me the neutral axis. So in this case, if this is the centroid C, then the z-axis is the neutral axis. And my distance, y, little y, is a distance that is always measured from the neutral axis and above. Okay? So I'm going to call a distance y. This distance y is measured from the neutral axis. If it's above the neutral axis, it's positive. The distance y. Measured from the neutral axis. If the distance y is above the neutral axis, then you ascribe a positive sign to it. If y then you ascribe a negative sign to it. Okay? If the bending moment m follows the sign convention, you give it a positive sign. Then you call it plus m. If the bending moment is opposite to the sign convention, which is concave upwards being positive, you call it as negative. These two are very, very important. Okay, so the distance, the bending moment. Everybody can see my writing clearly, people in the back. Okay, and audio is fine too. Okay, all right. Then we derived a formula for the bending stress, and I'm going to present that formula here based on the fact that we did it last time. First things first, I'm going to slice this beam at some point. Okay, so I'm going to cut this beam. Let me call it as point A. Let me call it as point B. Point C is the centroid. And I cut this beam and I draw a three-dimensional view of this beam. Okay? So that the x-axis is going to be pointing into the page. Okay, so this is the cross-section of the beam that you're seeing. I have the centroid placed right here. Okay, so this is the centroid. The axes that I'm going to be seeing is the cross-sectional axes y and z. The z-axis is the neutral axis. The x-axis is pointed into the page. Okay, right-hand rule. This is the x-axis along the length of the beam. Does this figure make sense to everybody? Okay, right-hand rule is if I go from the y-axis to the z-axis, I should get the x-axis. Okay, so fingers of my right hand aligned with the y-axis, my palm faces the z, I curl my fingers, thumb is pointed into the board. Okay, so the z-axis is into the page of the problem or the board. The bending moment is along which axis? It's about the z-axis, but it's pointing, if I'm looking at the bending moment on this side of the cut, then the bending moment is pointed into the page. Right? Does this make sense to everybody? Curl the fingers, it is pointed into the page. So this is opposite to the positive z direction, so bending moment is directed this way, so this is capital M. And so key thing, the bending moment is always going to be directed along the neutral axis. You see that, right? This is the neutral axis. This is the bending moment. The bending moment is always directed along the neutral axis, either in the positive or the negative direction. So bending moment that's one thing. The expression for the bending stress is the following. Sigma is minus m y by I neutral axis, where y is distance along the y-axis from the neutral axis. Okay, so here is the distance y from the neutral axis pointing up. I and A is the moment of inertia about the neutral axis. and each of them have a role to play. When we derived this formula, this moment m was taken to be along the positive sign convention. Which means that if I choose a distance above the neutral axis, let's say I choose some point here, what is the state of the stress? What is the state of the bending stress? It is going to be minus m times the distance y, if I call this as some distance y, divided by INA. This is a geometric property. The neutral at the moment of inertia is a geometric property. It is constant for a given cross section. It does not change. Okay, so this guy is fixed. The only things that can flip their signs are the bending moment and the distance y. If the distance y is taken above the neutral axis, is y positive or negative? Is this y positive or negative?
Positive.
Has to be positive. The bending moment m is positive or negative? Positive, because I am choosing it based on the sign convention. This is concave upwards. Which means that if I am choosing a point here, what is the state of the bending stress? Is it tensile or compressive?
Compressive.
Please look at the formula. This is positive, this is positive. If this is negative, it means that it is a compressive stress. Does this make sense to everybody? I still keep hearing tensile. Is this something that you want me to talk about again? Here is an example from last time. I don't know to break the keyboard, but this is your cross section. Okay? The hand axis that I'm placing here is my neutral axis. Okay? The way the bending moment is applied is that it's taking the top, taking the bottom, pushing the top inside, pulling the bottom outside. If something is being pushed, it's in compression. If something is being pulled, it's in tension. Okay, so which means that if I'm choosing a point above the neutral axis, if the moment is according to the sign convention, this is going to be in a state of compression. Likewise, if I choose something below the neutral axis, it's going to be in a state of tension. And you see, it automatically makes sense if I call this as y1, okay? And I call this distance as y2. Now, is y2 a positive or a negative distance? Since y2 is below the neutral axis, y2 is going to be negative. Capital M is still positive because it's according to the sign convention. So I have a negative times a positive times a negative, so that the total stress itself becomes positive, and so I have a tensile stress right at that point. Okay? And as we solve problems, this will become a little more clear. And we can draw the state of stress. I think we've drawn it last time. You can show it on the cross section, or you can show it on a three-dimensional view. So my stresses will be compressive on the top, all the way up to the neutral axis, and tensile here. Okay, and they are going to change linearly. Okay, so this is going to be my stress distribution. And we're going to do this for multiple problems. Okay, yes, question.
I just have a quick question. I'm having a difficulty grasping how you took the bending moment from the 2D shape and you use it to create a convention for the 3D shape. Like, why is it pointing that way?
Oh yes, okay, sure. We can bring it up. By the way, I'm going to remove this here. Okay. These are topics for the exam. Okay. Right, so what I'm doing is the following. Oscillatory motion. You're doing dynamics, you must have been getting vibrations by now. Or not. Alright. What I'm doing is the following. Okay, I'm cutting this vibration, breaking it up into two pieces. Okay, so I take this piece and this is my bending moment, and so I'm going to have an equal and opposite bending moment there, which means on this side of the piece, I'm going to have a bending moment M, which will be equal and opposite to whatever is happening here. And what I have done there is I have taken this guy, taken that guy and flipped it and drawn it there. Okay, so here, y-axis, z-axis, this is my bending moment, okay, this is my x-axis, and my y-axis. Does this make sense? So this is what we've drawn. This is the viewpoint. Okay, so every time we solve a problem, we'll be doing something of that sort, where we'll be cutting the beam, we'll be breaking it into two pieces, depending on the location where we're interested in. Most of the times I'm interested in the location where the bending moment is a maximum. Okay? And if I look at it this way, then it looks as if the top portion of this half is pushed into the page due to the bending moment. The bottom half is coming out of the page due to the bending moment. So the top is in compression, bottom is in tension. If it were against the sign convention, then the top would be in tension and the bottom would be in compression. Okay? Alright. And I'm going to take off this portion as well. And one very last thing. In this figure, what is the direction of the bending stress? Is it along the x-axis, the y-axis, or the z-axis? What's the direction of the bending stress?
X.
It's pointing into the page or out of the page, right? So which means that in the presence of the cross section, that's going to be the x-axis. So whenever you talk about normal stresses, what are the causes of normal stresses? Axial loads. And caused by bending moment. The normal stress caused by the axial load, you call it as axial stress. But they are normal stresses. They are normal to the cross section. The stresses caused by the bending moment, you call it as a bending stress. Both of these are normal to the cross section. Normal means perpendicular to the cross section. Normal or perpendicular to the cross section. But there is a problem. I can have bending stresses. If I look at a three-dimensional body, I can have bending stresses on different portions of the body. Right? I can have a bending stress on one cross section which is along the plane of the body. I can have bending stresses on another cross section which is out of the plane of the body. So when you look at three-dimensional state of stress, which is what we're going to be going towards, I need to have a sense of directionality for the stress. So this is what we typically do. We call all normal stresses by the following name. Sigma I, where the index I can be either the x-axis, the y-axis, or the z-axis. So I can be x, y, or z. Why are there two indices there? Is because the first index I represents the direction of the stress, This first index there represents the direction of the stress. And the second index represents the direction of the area normal to the cross section. Look at the cross section. It's along the y and the z axis. What is the normal to the cross section? If I have a cross section which is the plane of the board, what's the direction normal to the cross section? X-axis, right? It's the direction that is perpendicular to the cross section. So the area normal for a cross section is the direction perpendicular to the cross section. That's the second index here. Direction of area normal, which is the direction perpendicular to the cross section. And so in this case, my normal stresses will be called as sigma xx. Okay, so each of them sigma xx. Okay, they will have a particular value. In this case, this will be sigma xx max, because I'm looking at the top or the bottom. They will be maximum either at the top or the bottom, maximum tensile or maximum compressive. If I'm looking at any other point, there will still be a sigma xx, but of a smaller magnitude. Okay? I'm going to remove the last figure here. All right. Now we're going to talk about transverse shear stresses. And we're going to call this as tau. For the time being, tau transverse. This is different from tau average, which you had seen at the beginning of the semester when we looked at average normal stresses due to normal loads. This was sigma average that you had seen before. Likewise, you had also seen a tau average. That is an average stress, or that is a gross estimation of what the stress is in the shear direction. We are going to correct that a little bit, and we are going to come up with a little